today about electrostatics. Have you had anything at all at your classrooms yet? No. Anybody? Teachers? Nothing. How about electricity? You've had a little bit about electricity. That helps. So what do you think? Does anybody give me a hint? What does electrostatics mean? There's no wrong answers. Tell me what you think it means.
Small charge of electricity.
A small charge of electricity.
Like when you touch something.
How about a big charge of electricity? How about lightning? Is that a big charge of electricity? It sure is. And lightning is probably the first time human beings noticed electrostatics, because they could see lightning bolts coming down from the sky and hitting various and sundry objects. And they ran into their cave and hid. So electrostatics, divide the word up into two parts. Electro, that tells you it has something to do with electricity. And static, what is static mean? We got any good language people? Static. Project your voice. If you're wrong, people will still hear you, but if you're right, you'll get noticed if you talk too quietly. So what is static?
Static is when two objects run together and they...
That's electrostatics. Static is simply not moving. It's electricity that's not moving. And we can generate that in a number of ways. You have a comment?
No, I don't.
Go ahead.
It's when a positive and a negative charge come together to form.
You're getting more complicated. Static simply means it's not moving.
Yeah.
That's all. So electrostatics is electricity that's not moving. When we plug in a light bulb and we haven't hit the switch on, the light bulb doesn't light. There's no electricity moving. But if I close the switch, we now have electricity circulating through the filament in the bulb. The filament gets hot and it lights. So that's not electrostatics, that's electricity. So we're going to talk electrostatics. So there's a number of ways we can generate electrostatic charge. How many people have walked across the living room rug and go to turn on their TV, if they're not using a remote, and they go to turn it on and poof, you get a spark? You have a comment?
I have had that happen to me before.
Yes, we all have. You're pulling your hair and you feel like crinkling sound. Pull your sweater up over your head and you get a little crinkling noise. You can sometimes even see a spark. That's all the creation of electrostatics. That means we are gathering electricity. And what do we really mean by that? Well, in the usual case, what we're doing is collecting electrons. And when we plug in that same light bulb into the switch, what we get is a current flow. It's not static any longer. And once we turn on this electrostatic generator, we will get a static charge on the generator, but as soon as I bring the grounding ball up to it, we'll get a spark, and we will have a current flow from the sphere to the grounding ball. All right, now, one of the best machines that they came up with is called a Van de Graaff generator. Anybody hear that term before?
No.
Sure you have. Anybody visit the Boston Museum of Science? And you didn't go to the Van de Graaff generator? All right, quiet. I'm talking again. All right. Van de Graaff was a man that went to MIT. And he was a graduate student. He was studying for his doctorate. And in 1935, he patented the basic idea of the Van de Graaff generator. It's a bit of an egotism, and he named it after himself. But anyway, the two patents that were important in the patent of the Van de Graaff generator I don't have a cold, I have allergies. And I would wager there's some mold in these cement walls. So you'll have to excuse me. But going back to Van de Graaff, in 1935, he applied and got granted the two basic patents. One was that he would bring the charge from ground up to the sphere on a continuously moving belt. Why did he bring the belt inside the sphere? That leads to the second of his patents. And what he did was he said, I'm not going to try to get the charge onto this sphere from the outside. I'm going to run the belt up inside the sphere. And if you can see the end of this, anybody that can't see it, I apologize, but 150 at a time is a little tough. What you have up here are what I call collector points. It's nothing but a bunch of wires sticking towards the belt. And what they are is they are collecting something. They are collecting electricity. In fact, in this particular polarity machine, they are collecting electrons. And he takes the electrons off the belt inside the sphere because inside the sphere there is no electric field. We're going to get to electric fields in a little bit. But there's a zero electric field inside of the enclosed sphere. When I say zero, definitely zero. It's a very, very low potential inside of the sphere. Okay. So those were the two things that Van de Graaff patented. I was 13 years old when it was first shown in public in 1938 at the New York World's Fair. And GE sponsored they put up the money to build that machine and to have it installed. And it was called, at the New York World's Fair in 1938, it was called Man-Made Lightning. And it's exactly the same machine that's still in use at the Boston Museum of Science. And if you go there the next time, you will see it. It's a Van de Graaff generator that's roughly 30 feet long or tall. And it has a huge upper sphere. Now, the interesting thing about the first time it was shown publicly, I was 13 years old and lived in New York. What an opportunity. And I went to the New York World's Fair at least 2 or 3 times. Through that summer, I went 2 or 3 times a week. And I always went to the GE exhibit to see the Van de Graaff generator and man-made lightning. You talk about coincidences. 10 years later, I was a student at Northeastern, and I went to work on my co-op job. If anybody's familiar with Northeastern, you know that it's a cooperative plan. And my co-op job was working for, of all people, Dr. Robert Van de Graaff. Just 10-year span of time. So that got me really involved in the Van de Graaff generator, and I learned an awful lot about how they worked and what they could do. So, what we want to talk about is the capability. What can we do with this particular Van de Graaff generator? Well, this is not the 30-foot high Van de Graaff that they've got at the Boston Museum of Science. But believe it or not, this machine can develop on a reasonably dry day, which this is not, and down into the basement. That is where any dampness that might be around is going to settle. We will still generate something in the order of 100 to 150,000 volts with this Van de Graaff. What determines the voltage? What would you think? Thinking logically, what do you suppose would determine the voltage that I can achieve on that Van de Graaff? Anybody got any thoughts? Remember I said there's no wrong answers.
Dryness of the air?
What?
The dryness of
That's a factor. Yes, that's a limiting factor. The basic thing though that controls the voltage.
Speed
You gotta speak up, I've got 85-year-old ears.
How fast the belt is going?
How fast the belt is going? Would anybody disagree with that? Well, the speed of the belt is a very important factor. But remember what the voltage is. The voltage is a collection of electrons on the sphere. So does the speed of the belt have anything to do with that? Only if I discharge it. So the speed of the belt is a factor in how long it takes to recharge it when I cause a spark to exist. So we still haven't gotten to what determines the basic quantity that determines the voltage that I get between here and here. They're pretty good hints between here and here. This is ground potential. This is the potential of the sphere. The length of the insulating column. If I make the column taller, stretch the belt a little further, I can get a higher voltage. There are some limiting factors. Some of the limiting factors are the moisture that's in the air. Another thing is what we have for losses due to things that surround the sphere. To make sure that it's working, I stopped in and got to let go, and I didn't notice they had a microwave oven not too far away, and we were not getting as hot a spark as I would like to have seen. And you can have losses very simply. I will demonstrate that. Well, let me just demonstrate the graph without further ado. You hear the sparking going on. The sparking is between the sphere and whatever is around. It may be from there, but let's see how close we can come and get the spark to. Now, where this is about 10 inches. In the atmosphere we've got in here, you get about 20,000 volts per inch. And the closer I get, what is happening, sparking is faster. That's determined by the speed of the belt and the width of the belt. If you go to the back again to the Van de Graaff that's in the Museum of Science, they have 3 belts. Each of the belts is about 3 feet wide. And when they get a spark, it's like man-made lightning, and it takes quite some time to recover and rebuild the charge on the sphere. On a good dry day, well, we're getting there. You can try it. I'm not sure. You have to put it completely off. There we go. Did anybody see that? There's our man-made light. All right. Let's settle down now. You can see that the charge, the voltage on the sphere is determined by the length of the column, the insulating column, or the distance you have the grounding ball from the sphere. Just as a slide, anybody want to guess what this handle is? Any people play golf? This is the handle from a golf club that was a fiberglass shaft golf club. Because we wanted an insulating handle. This is tied to ground, which is what a base is. And the end of that is a brass doorknob. I say these things because I have one, unfortunately, which I couldn't find. It's lost somewhere in my attic. And you can build a Van de Graaff